Hey everyone, welcome to this explainer. If you're gearing up to sit for your private pilot ground exam, you are exactly where you need to be. Today, we're going to give you the specific exam-ready knowledge you need to absolutely crush the questions on one of aviation's most notorious phenomena. We're breaking down the science, the scenarios, and the life-saving procedures you've got to know. It's all perfectly packaged so you can ace your test and, more importantly, fly safely. You know, crazy enough, the most dangerous threats in aviation are very often the ones you can't actually see out your cockpit window. I mean, we spend so much time looking out for clouds, terrain, other traffic. But what happens when the hazard is entirely invisible? We're talking about wake turbulence. It's this violent hidden force left behind by aircraft that can literally flip a small plane upside down in a heartbeat. Okay, let's dive right into our concept to application blueprint. First up, the anatomy of a vortex. Second, peak turbulence conditions. Third, helicopter downwash. And finally, the golden rules for avoidance. Starting off with Section 1, Anatomy of a Vortex. So before we can dodge this invisible hazard, we really have to ask ourselves, what actually causes it in the first place? Well, it all comes down to the fundamental physics of how your airplane leaves the ground. Every time you generate lift, your aerofoil is flown at a positive angle of attack. This creates an absolutely crucial pressure differential. The pressure above the upper wing surface is less than atmospheric pressure, so a low pressure zone. Meanwhile, the lower wing surface has pressure equal to or greater than atmospheric pressure, giving us a high pressure zone. Now, this pressure difference is what holds you up in the air, right? But it definitely comes with a chaotic side effect. Now, here's where the behavior of that air gets really interesting. Physics tells us that air always desperately wants to move from high pressure toward low pressure to balance things out. But the fuselage blocks the air from moving straight up, so it seeks the path of least resistance. And that path? It's right around the wingtips. The high-pressure air from the bottom literally spills over the edges to the low-pressure top, and it creates the swirling whirlpool of air called a wingtip vortex. Let's picture how that vortex takes shape. Imagine a lateral spanwise flow. The air pushes outward away from the fuselage on the bottom of your wing, curls right upward around the tip, and then pulls back inward toward the fuselage on the top. When this aggressive curling action combines with the wash from the aircraft actually moving forward, it forms a violent, fast-spinning trailing vortex stretching way out behind the plane. And hey, for your exam, remember this specific term. All the energy your engine spends producing the swirling turbulence, that is the exact definition of induced drag. Moving right along to Section 2, Peak Turbulence Conditions. Now that we know how these violent spirals form, let's look at the specific conditions that make them incredibly dangerous. This is a guaranteed exam question, by the way. I want to pose this direct question to you right now to get you thinking. If vortices are caused by the pressure differential of lift, when are wingtip vortices at their absolute strongest? Lock this phrase into your memory for exam day: heavy, clean, and slow. Why? Because when a large aircraft is really heavy and moving slowly, it requires a massively high angle of attack just to stay in the air. That high angle of attack creates the maximum pressure difference between the top and bottom of the wing, which forces a massive amount of spillage over the tips. And clean? That just means the flaps and landing gear are retracted, allowing that vortex to form perfectly without being broken up by aircraft components hanging down. Let's break down the exact mathematical relationships the examiners want you to know. So the crucial point here is this: aircraft weight is directly proportional to vortex strength. Basically, the heavier the plane, the harder it works to fly, and the stronger the vortex. On the flip side, though, aircraft wingspan and speed are inversely proportional to vortex strength. A longer wingspan spreads out that pressure differential, and a faster speed lowers the required angle of attack. So both of those things actually decrease the strength of the wake turbulence. Real quick, before we move on to helicopters, I was actually going to tell you a joke about a wingtip, but I was worried it might drag on. Get it? Induced drag? Oh man. All right, I'll stick to the aviation instruction. Let's smoothly transition over to our rotary wing friends. Section 3, Helicopter Downwash. So rotary wing aircraft follow the exact same aerodynamic rules we just talked about, but they present some pretty unique hazards. When you're taxiing or flying near a hovering helicopter, remember the magic number 3. You absolutely must maintain a distance of at least 3 rotor disc diameters from a hovering helicopter to safely avoid the crushing effects of its downwash. That invisible column of air pounding the ground is definitely no joke for a light aircraft. But listen up, here's a major warning for you. When a helicopter transitions from a hover into forward flight, that downwash transforms. It morphs into a pair of high-speed trailing vortices, exactly like a fixed-wing airplane. And remember our heavy, clean, and slow rule from earlier? Because helicopters operate at exceptionally slow forward airspeeds compared to airliners, their trailing vortices are incredibly strong. Never, ever underestimate a helicopter's wake just because the aircraft is smaller than a jumbo jet. Okay, Section 4, Rules for Turbulence Avoidance. Understanding the physics is great for the written exam, sure. But now let's get into actionable, life-saving procedures for when you're actually in the cockpit. Let's walk through the exact chronological steps for taking off behind a larger aircraft. Remember, vortices begin the absolute moment the preceding aircraft generates lift, which is right when its nose wheel leaves the ground. So, step 1, note their rotation point on the runway. Step 2, plan your takeoff roll so you rotate prior to their rotation point. And step 3, once you're in the air, you must climb above their flight path. Vortices sink over time, so staying above them keeps you up in the clean, safe air. Now let's contrast that takeoff procedure with the landing procedure. Wake turbulence effectively ends the moment the preceding aircraft's wheels touch down and they stop generating lift. So step 1, fly your final approach above the preceding aircraft's glide path. Step 2, note their exact touchdown point. Step 3, float past that mark and ensure you touch down after their touchdown point. Basically, you're flying right over the invisible hazard and landing in the safe zone where the vortices have already stopped forming. But what about when you're just cruising or on an approach path? Keep the number 1000 in mind. You must avoid following another aircraft on a similar flight path within 1,000 feet of altitude. Because those dense wingtip vortices sink at a rate of several hundred feet per minute, the turbulent wake of a heavy jet can drop right down into your altitude if you're flying directly beneath them. Now, let's add weather to the mix. Wind acts like a giant conveyor belt for wake turbulence. Wingtip vortices literally drift with the wind, moving at the exact speed of the wind. To put that into perspective for you, a gentle 10-knot crosswind causes these invisible tornadoes to drift about 1,000 feet laterally in just 1 minute. That means a hazard generated on one runway can blow right over to an active parallel runway. You absolutely always have to consider wind speed and direction when visualizing where that wake is moving. And finally, if you find yourself in a situation where you're just unsure of the preceding aircraft's exact takeoff or landing point, or maybe the winds are perfectly aligned to hold a vortex right over the runway, just fall back on the 3-minute rule. Simply request a delay from ATC or hold your position and wait approximately 3 minutes. That gives the atmosphere enough time to naturally break down and dissipate the turbulence, giving you a really solid margin of safety. So I want to leave you with this final provocative thought to really test your airmanship. Are you flying the plane, or is the invisible air flying you? A great pilot uses their mind to see what their eyes cannot. If you master the physics of wake turbulence and apply these avoidance rules, you're not just going to pass your ground exam, you're going to be a drastically safer pilot out there in the real world. Best of luck on your PPL exam, everyone. Make sure to like and subscribe for more ground school explainers just like this one. Fly safe.